This module, we will be studying about continuous charge distribution. Electric fields are produced by continuous charge distribution on the surfaces of the bodies of finite size. A few examples of practical situations are a line charge distribution, a sheet of charge, or a volume charge distribution. Now, to evaluate the electric field at a point due to these charge distributions, we assume the entire charge distribution to be made of infinitesimal small elements, and the electric field strength at any point in the electric field will be equal to the vectorial sum of the electric field strengths due to each such small element. Let us look at the like charge distribution of length L carrying a charge Q as shown. If we consider a small element of such a charge distribution having a charge delta Q and of length delta L, the linear charge density lambda of such an element is equal to delta Q by delta L. Since it is the charge per unit, the SI unit of linear charge density, lambda, is Coulomb per meter. It is a scalar quantity. If a line charge distribution is carrying a non-uniformly distributed charge, then its linear charge density for an individual element is equal to delta Q by delta L. If a conductor of length L is carrying a uniformly distributed charge Q, then its linear charge density is equal to Q by L. Now, let us consider a sheet of charge carrying a total charge Q on a surface area A. In such situations, the electric field strength at an imaginary point P can be calculated by assuming the charge distribution to be divided into infinitesimally small area, each having an area delta A and a charge distribution delta Q. Surface charge density, sigma, is the charge per unit surface area. Therefore, the surface charge density for an individual surface element is expressed as sigma is equal to delta Q by delta A. It is a scalar quantity measured in Coulomb per meter square in SI unit. If the charges are non-uniformly distributed, surface charge density for an individual surface element is expressed as sigma is equal to delta Q by delta A. If the charges are uniformly distributed over the surface, then the surface charge density sigma is equal to Q by A. Now, let us consider a volume charge distribution. Consider a volume V carrying a charge Q. Let us assume that the total volume is divided into a number of small elements, each of volume delta V having a charge delta Q. Then, volume charge density or charge density rho of such a volume charge distribution is defined as the charge per unit volume. Thus, rho is equal to delta Q by delta V and is measured in Coulomb per meter cube in SI unit. It is a scalar quantity. If charges are not uniformly distributed, the charge density rho for an individual volume element is equal to delta Q by delta V. If the charges are uniformly distributed, the volume charge density of the conductor is expressed as rho is equal to Q by V. Now, consider the small volume element delta V of charged distribution carrying a charge delta Q. We know that the charge density rho is equal to delta Q by delta V. Thus, the charge on the volume element is then delta Q is equal to rho delta V. The position vector of the volume element delta V with respect to the origin O is R. Consider a point T in the electric field of volume charge distribution, which is at a distance of r dash from the volume element delta V. The electric field strength at point T due to the volume element is delta E is equal to 1 by 4 pi epsilon naught delta Q by r dash square into r dash cap, where r dash cap is the unit vector in the direction of the straight line from the volume element towards the point T. This can be written as delta E is equal to 1 by 4 pi epsilon naught into rho delta V by r dash square into r dash cap. Now, the electric field strength E at D due to the total volume charge distribution is equal to the vectorial sum of the electric field strengths due to all individual volume elements. Since there will be many infinitesimal volume elements at varying distances from the point T, hence, to obtain the electric field strength E due to the total volume charge distribution, we integrate delta E within suitable limits a to b under the assumption that the volume elements have very small volume tending to 0.